95% of the universe is invisible to you, not because it's far away or too dim, but because it doesn't interact with light at all. Yet its gravity is sculpting galaxies, steering galaxy clusters, and quietly deciding the fate of cosmic structure on the largest scales. When you look up at the night sky, every star, every glowing nebula, every galaxy you can see is just the tip of an iceberg. The visible universe is the foam on top of a much deeper ocean. And most of that ocean is something we call dark matter, a form of matter that passes through you, the Earth, and entire galaxies, almost as if they weren't there, but still pulls on everything with gravity. Dark matter is, at its core, a bookkeeping problem. When astronomers in the 20th century measured how fast stars orbit in galaxies and how galaxies orbit in clusters, the numbers simply didn't add up. There wasn't enough visible mass to produce the gravity required to hold everything together. In the 1970s, Vera Rubin and others measured rotation curves of spiral galaxies, how orbital speed changes with distance from the center. If only visible matter mattered, outer stars should move more slowly, like planets in our solar system. Instead, the speed stayed roughly flat, even far beyond the bright disk. It was as if each galaxy was embedded in a huge, invisible halo of extra mass. So what is dark matter? First, what it's not. It's not just regular stuff hiding in the dark, not faint stars, cold gas, or black holes. Those things exist, but we can estimate their total mass from the light they emit, or the way they absorb light. They fall far short of what's needed. Dark matter is a form of matter that, as far as we can tell, does not emit, absorb, or scatter electromagnetic radiation. It doesn't shine, it doesn't glow in infrared, it doesn't block starlight like a dust cloud. We infer its presence only through gravity, the way it bends the paths of stars, gas, and even light itself as they move through the universe. To understand how it works, imagine a galaxy cluster. Hundreds of galaxies bound together by gravity, swimming in hot gas, tens of millions of degrees hot. That gas glows in X-rays, and from its temperature and motions, we can estimate how deep the gravitational well must be to keep it from evaporating into space. In the 1930s, Fritz Zwicky did this for the Coma cluster and found something shocking. The visible galaxies didn't provide nearly enough mass. He called the missing mass Dunkel Materie, dark matter. Decades later, gravitational lensing, where massive objects bend the path of light like a cosmic magnifying glass, confirmed that galaxy clusters contain far more mass than their luminous parts alone. Gravitational lensing is one of the cleanest pieces of evidence. When light from a distant galaxy passes near a massive cluster, its path curves, distorting the background galaxy's apparent shape. By measuring these distortions across the sky, astronomers can reconstruct how mass, including dark matter, is distributed even when nothing visible is there. These maps show that dark matter forms vast, diffuse halos around galaxies and clusters, extending far beyond the visible edges. On even larger scales, simulations and observations reveal a cosmic web, filaments of dark matter stretching hundreds of millions of light years, with galaxies forming like dewdrops along these invisible threads. Here's where dark matter becomes more than a curiosity. It's the scaffolding of structure in the universe. In the early universe, tiny quantum fluctuations in density were imprinted into the hot plasma. Dark matter, which doesn't interact with light, began clumping under gravity very early, forming dense regions while normal matter was still tightly coupled to radiation. After about 380,000 years, when the universe cooled enough for atoms to form, normal matter decoupled from light and could start falling into the gravitational wells that dark matter had already built. Without dark matter, the cosmic microwave background tells us there simply wouldn't have been enough time for galaxies and clusters to grow as large as we see them today. On the scale of a single galaxy like the Milky Way, dark matter dominates the mass budget. Our galaxy's visible disk, stars, gas, dust, is embedded in a roughly spherical dark matter halo that may extend several 100,000 light years. The total mass of this halo is thought to be about 1 trillion times the mass of the Sun, far outweighing all the stars you can see. You, right now, are moving through this halo, The Earth orbits the Sun at about 30 kilometers per second, and the Sun orbits the galactic center at about 220 kilometers per second, plowing through a sea of dark matter particles. If dark matter is made of particles, then trillions of them may be passing through your body every second, and you don't feel a thing. That brings us to the big question. What is dark matter made of? The leading idea is that it consists of new, as yet undiscovered particles that interact very weakly with normal matter. One class of candidates is WIMPs, weakly interacting massive particles, with masses perhaps tens to thousands of times that of a proton, interacting via gravity and maybe the weak nuclear force. To find them, experiments bury ultra-sensitive detectors deep underground, shielded from cosmic rays. These detectors are vats of liquid xenon, or crystals cooled to near absolute zero, waiting for the faintest possible recoil as a dark matter particle bumps into an atomic nucleus. So far, they've seen only tantalizing hints, and many claimed signals have faded with more data. Another candidate is the axion, a hypothetical ultralight particle originally proposed to solve a problem in quantum chromodynamics. Axions would be so light and numerous that they'd behave more like a classical field than individual particles. Experiments search for them by trying to convert axions into photons in strong magnetic fields, listening for a tiny, narrow-band radio signal from the dark. There are also more exotic ideas: sterile neutrinos, hidden sector particles, even the possibility that dark matter is not particles at all, but a modification of gravity on large scales. Modified gravity theories like MOND tweak the laws of motion to explain galaxy rotation curves without extra matter, but they struggle to match the full range of cosmological observations, as well as particle dark matter does. Despite all this, one thing is clear: dark matter matters. It affects how galaxies merge, how galaxy clusters collide, and how the universe expands. In the famous Bullet cluster, two galaxy clusters have passed through each other. The hot gas, which makes up most of the visible mass, collided and slowed down, but gravitational lensing shows that most of the mass kept going with the galaxies. This separation between visible matter and gravitational mass is hard to explain with modified gravity alone, but fits naturally if most of the mass is in a collisionless dark matter component. It's like watching two ghostly clouds pass through each other while their visible gaseous parts crash and heat up in the middle. Yet, for all its successes, the dark matter paradigm still has puzzles. On small scales, simulations of cold dark matter predict more small satellite galaxies and denser central cusps than we seem to observe around galaxies like the Milky Way. Astrophysicists explore solutions. Perhaps feedback from supernovae reshapes the inner regions. Or dark matter has a tiny amount of self-interaction, or it's slightly warm rather than perfectly cold. And we still haven't detected a single dark matter particle in the lab. The Large Hadron Collider has not yet produced any convincing dark matter candidates. Direct detection experiments keep pushing down the possible interaction strength. Each non-detection rules out a swath of parameter space, forcing theorists to refine or rethink their models. So we end where we began, with an enormous hole in our understanding. We can map where dark matter is, we can see what it does, we can simulate a universe full of it, and get something that looks remarkably like the real cosmos. But we don't yet know what it is made of, or whether our deepest theories of space, time, and gravity are missing a crucial piece. Until then, every star you see is a reminder that most of reality is still in the dark, and that's exactly the kind of mystery we love to explore here on TerraNova.